Good evening. Welcome to our third class. In this class, we are again going to discuss the basics of probability in order to understand the concepts of noise from the subject communication systems. So, in the first class, we have covered the basics of probability, the properties and axioms. In the second class, we have covered the binary symmetric channel, and in this class, we will be going to cover the definitions of various terms. These terms are like what is the probability distribution function, what is the probability density function, so what is the probability mass function, and related definitions. And also we are going to cover the definition of a random variable. So we'll start with the definition of random variable. Random variable, it is simply defined as whenever the experiment is performed, the experiment will be giving us the outputs. The output will be whenever we take the experiment, it is an event. Conduction of experiment is an event. The outcome can be different. It is random because we don't know the output beforehand. So just like tossing a coin. So whenever a coin is tossed, the output can be heads, can be tails. We don't know that beforehand. But mapping of these outputs, the possible outputs, whenever the possible outputs, let me put it down here, whenever the possible outputs of an experiment are mapped to some real numbers, then it is called as random variable. So we can right now we can define random variable as a function. So it's a function that maps the outputs of the random experiment to some real numbers. This function that maps the outputs of the random variable to various numbers, to various real numbers, is called as random variable. So let me take the example. So the most simple example is tossing of a coin. So whenever a coin is tossed, the output could be heads, the output could be tails. So if suppose heads is mapped to some real number, let us say 0, and tails is mapped to some real number 1. So this mapping function is called our random variable, and it is random because we don't know the output beforehand. Only we know the output after performing the experiment, and so it is called as random. So now let us go to the concept of probability mass function. So the probability mass function will be developed again from here itself, from tossing the coin itself. But let us see the subject now. Let us see the concept in terms of probability mass function. Now we have conducted the experiment. The experiment is tossing of a coin. The experiment is tossing of a coin, and the outputs are, it can be heads, it can be tails. The probabilities of occurrence of heads is half. The probabilities of occurrence of tails is half for a fair coin, right? There may be some problems or some situations where the probability is not equal to half. In that case, the probability of getting heads, let us put as p. Then what happens? The probability of getting tails is simply 1 minus p. This is a little bit this is simply by observing or by applying our intuition we will understand, because there is only two events, one is heads and the other one is tails. If the probability of head is given by p, then obviously the probability of tail is 1 minus p, because the outcome is certain. Outcome is certain. So the probability of outcome is 1, because outcome is certain. That can be heads, that can be tails. So if probability, but the outcome is happening once a coin is tossed, we will be absolutely getting the output. But only thing is that that can be head, that can be tail. If the probability of head is given by p, then obviously the probability of tail is given by 1 minus p, because the probability of outcome can be written as probability of head plus probability of tail minus probability of head intersection tail. But we know what we have known yesterday also, we have discussed about something called as mutually exclusive events. Whenever the property of mutually exclusiveness is applied, the intersection will be 0. Here it is absolutely applied. The reason is that if heads is occurring, then tails will not occur, and if heads is not occurring, absolutely tails will occur. So the third term is going to be becoming 0, and probability of outcome is certain because the experiment is performed. Outcome can be anything, but the probability of outcome is simply 1 because outcome is certain, and outcome is equal to probability of heads. Let us take it as p, then probability of tail is simply given as 1 minus p. Yesterday we have seen the same concept in the reception side of the binary symmetric channel. Well, probability of reception is absolutely 1 because the signal has to be received. Probability of reception has to be 1, and that can be equal to probability of error plus probability of transmission. Correct, I mean without error. So from this one we can understand that if probability of error is given as p, then probability of transmission without error, let me write it like this, is simply given by 1 minus p, because 1 is the probability of reception. The signal is received, whether that can be error or that can be correct. If that is error, then that is not correct. If that is correct, then that is not error, because error and correct transmission are mutually exclusive. If one occurs, the other doesn't occur. Yesterday we have applied in order to this particular concept, in order to obtain the probabilities as p and 1 minus p for the binary symmetric channel, if you remember. But now let's come back to our concept of today. So let's end the binary symmetric channel here. Yesterday, later we, if it is required, we may take another class regarding this one. If time permits and people demand, we will see later. Now let's come back to our tossing of the coin. So we have already seen here the probability of outcome here. If you come to this line, let me put the equation number 1. The probability of outcome is always 1. If the probability of obtaining heads is taken as p, then absolutely the probability of obtaining tail is 1 minus p, because these are the two events that are mutually exclusive. So now let me put it in the form of graph. Here, instead of p, let us take it as half. So even when we started the concept of probability mass function, we have taken the fair coin. In the fair coin, what is happening is the p itself is half. That means the probability of occurrence of head is half, probability of occurrence of tail is half. So that's the coin in our pocket if we just see. So now let me put the probabilities of occurrence of heads and tails on a graph. So let me go to the next page. So we have taken a coin. So let me put again the heading as the name of the experiment. So tossing of the coin. Now we have told that the probability of occurrence of the head and the probability of occurrence of tail are simply equal, and they are equal to half, as it is a fair coin. Now what is happening is, let me put actually I have already told you what is a random variable. Random variable is mapping the outcomes of the experiment to some real numbers. So here in this random variable, I have mapped the occurrence of head to a real number 0 and occurrence of tail to a real number 1. It is not like a rule that we should map that to 0 and that to 1. We can also map to some random real numbers, but here let me put it simple, and I have taken, because there are only two outcomes, I have put it simple, and I am taking it one as 0, the other one is 1. So now the probability of occurrence of head is half. So probability of event 0 is simply half. Then the probability of occurrence of tail is half. So probability of event 1 is again half. So now let me draw a real scale. Here this is a real scale. Here various numbers are there, but we are only using 0, and we are also using only 1. The reason is that only 2 outcomes are there in our experiment. Now I am putting 2 impulses here. One is at 0, the other impulse is at 1. Now what I am doing is I am giving the area of the impulse as the value of the probability. So whenever the area of the impulse is actually indicated by a number that here hit half, here it half, it indicates the area of this impulse. Similarly, this half indicate the area of this impulse. Whenever the probabilities are given by areas of the impulses at the particular real numbers which are mapped to the outcomes of those experiments, such a plot of impulses is actually called the probability mass function. This is called the probability mass function. So now let me take you to the definition of a probability distribution function. Here we have seen what is the probability mass function. Simply it can be told PMF. Now let's go to the definition of probability distribution functions from here. As a continuation of this topic only, we are going to cover probability distribution function. So the probability distribution function, here probability distribution function is a summation of the probability mass functions along the real line. If I give it as in mathematically, so if I take it as p of x, then p of x, usually it is even more up correctly, it is taken as fx of x, not p of x, fx of x. So this is actually the probability distribution function, and fx of x mathematically is given by fx of x is equal to summation minus infinity up to x p of x is equal to xi. Here xi is equal to xi. So whenever these impulses are added in this up to x, say for example on this time on the scale, on this real scale where we have drawn the probability mass function, if x is taken at some point, so here let us take this point as x. So now this x corresponds to this x inside the distribution function. So fx of x is equal to summation minus infinity to x p of x is equal to xi. So if I am adding all the impulses up to this point, so from extreme left, that means from minus infinity along the graph up to x, if all the impulses I have added, then I will be getting the probability distribution function fx of x. So this is the mathematical definition of probability distribution function, and it is a sum of the probabilities of all the impulses, the sum of the probabilities, it is sum of the weights of all impulses from minus infinity up to the point of consideration x. It is given by the probability distribution function fx of x. Now let us see how its waveform will be looking. So its waveform will be taking this shape. Say for example, let me first again draw the distribution density function, I mean the probability mass function, which I have given it in terms of impulses which I have put above. Say for example there is some this time I am taking some kind of random probability mass function. We are not worried about the function here, we are only worried about the waveforms. Now this is actually the probability mass function. So there are various probabilities here. So for tossing of a coin, it is half and half, but in this case I have to give some values to this, but let me take some random values like ABC, I mean small abc, small b, small c, small d, small e, and small f. So this probability mass function is having various probabilities which are represented by the impulses, and these impulses are having the weights, I mean the area of the impulses are called the weights, right? Those weights are a, b, c, d, e, f. So now if I am trying to draw the probability distribution function If I have taken the point x as here, now this is actually in terms of probability distribution function, it is given by fx of x, and mathematically it is given by minus infinity to x, p of x is equal to xi. So if I am adding all the impulses, weights of impulses up to this point x, I am going to get the distribution function. So its plot, now let us see what is the plot of that fx of x, or the probability distribution function. So here right now, addition of the impulses up to this point, there is no impulses, but suddenly at this point there is an impulse whose weight is a. So here it is going to increase because you are summing the impulse. It will be reflected as a step in the distribution function. After addition of the impulses, we are going to, after the summation of impulses, we are going to get the step function in the distribution function. So from from here, it is going to carry the value of a. It will be attached to the value of a. After that, up to this point where b has occurred, at this point again it will be a plus b, because a is already being carried and it is summed up to for the impulses, and at this point the magnitude b is added, and at this point the magnitude c is added. So the magnitude will be a plus b plus c. So from here up to here, at the point d, the magnitude will be increased to a plus b plus c plus d, and so on. So from this, what we understand, that probability distribution function is taking staircase waveform. So this thing just we will have to remember. So the probability mass function will be having a train of impulses, and probability distribution will be taking a staircase waveform. So this is up to the probability distribution function. Now from here, let us go to another related, just as a continuous just take as a continuity to this concept. We are going to the next topic, that is probability density function. This one we will be analyzing using one probability density function using one kind of standard distribution, that is rectangular distribution. Okay, let's go further, but here let me start what is a probability density function. Earlier we have seen what is a probability mass function. Probability mass function is the function that is representing the probabilities in the form of train of impulses at the appropriate points on the real scale. But probability density function, here it in the probability mass function, we can directly see that the outputs of the experiments are discrete in nature. So the output of the random variable, like tossing of the coin, I have put the heading of this page. Here it is discrete in nature. The reason is that the output can be only taking two values, one is head, one is tail, so it is discrete. But there are some events where the outputs are, or the probability of occurrence of the outputs is not discrete. It cannot be individually given as half and half, separately given as half and half, but it is of continuous nature. Such a functions are such a probability density, such a probability functions are actually called as probability density functions. The probability of such continuous nature is given by probability density function. So for example, there are various examples like Gaussian distribution, but we will come back to the examples later. But let me start with a standard probability density function, rectangular, with as an example rectangular density function. Usually the rectangular, are some people you may call it as uniform density also. So this uniform density, if we observe, simply there will be the real scale, and there will be taken 2 points A and B, and the probability between A and B is actually the taking the form of a rectangle like this. So here the probability between, let me give the symbol fx, because x is the random variable here. This probability, that means the output of the experiment, is between A and B, and the output probability is having a constant value between A and B, let that be k. we will get the value of the k, we will derive the value of the k right now, but let us see the probability density function now. So this is giving the standard rectangular probability density function. Here if we observe, there is one critical difference between discrete and continuous random variable. In the discrete random variable, where the outputs are discrete, we are able to define exactly what is the probability at 1, like probability of head is equal to half. We are able to, probability of head is actually given by event 0 on the real scale. But when it comes to our continuous distribution, if a single point is taken, say for example at this point, let this point be p. If a single point is taken, then p of p is not defined. We can say p of p is actually 0. A single point p, if it is chosen, then the probability of that particular point is simply 0. In such a case, what we have to do is we have to take an interval. Here the probabilities are defined only for intervals. Say for example, if we want a probability at point p, then what we do is it has to be given by integration over the probability density function from 2 points, exactly p minus to p plus. This p minus and p plus are just separated from p infinitesimally. That means there is very little difference on the scale from p and p plus and p minus. Say for example, if you consider the scale, p minus is just toward the left of p and p plus is just toward the right of p. So whenever the probability density function is integrated between p minus to p plus, the probability, let me put the value of probability density function later, but for now let me put pdf here, dx. So when if we have integrated the probability density function from minus p to p minus to p plus, we get the probability at p, because the probability at p individual point is not defined when probability density function is continuous in continuous case. Okay, now let us go to the next slide here. So the probability at an individual point is not defined, but the probability at an individual point can be calculated by calculating the integration of probability density function from the lower limit to upper limit, where lower limit and upper limit are extremely near points to p, towards its left side and towards its right side. So this equation will be giving that probability of at a point p. Now again, let's come back to the probability density function. Now here now we will be calculating what is the value of k. Here we have taken an example of our probability density function as a rectangular function or uniform density function. There are various other functions, like, let me just name them. Each one we will be discussing later. There is Gaussian, there is exponential, there is Rayleigh. There are various real world events will be using these probability density functions. We will also see them, and some others are there. We will be discussing them each one. Now let us see what is the value of k. In order to calculate the value of k, we need to understand two important properties of probability density function as also probability mass function. Two important properties, let me name them. The two important properties of probability mass function, let me put it as PMF, and also probability density function, let me put it as PDF, are as follows. First one is fx of x, the probability density function at any point is greater than or equal to 0. At any point, the probability density function is greater than or equal to 0. Similarly, for probability mass function, the probability at any point is greater than or equal to 0 if that point is lying on the real scale and there is one event corresponding to that point, then the probability is greater than 0. If there is no event corresponding to that real point, then probability is equal to 0. But probabilities are always greater than or equal to 0, but they are never negative. Probabilities are never negative, so obviously the probability mass function and the probability density function are never having negative values. The second property is, for the probability density function, the integration of the probability density function over the entire real scale is equal to 1. Here this property is indicating that the probability of sample space, it is simply indicating that probability of sample space is 1, because probability density function is giving the probabilities of various events that are happening in the sample space itself when the entire sample space is integrated, like from minus infinity to plus infinity, the entire sample space is integrated. The resultant probability is obtained as 1, because here we are using the entire sample space. And similarly, the counterpart, if you are coming to probability density function, here we can say integration of from minus infinity to plus infinity of probability mass function is simply is equal to 1, because we have covered the entire sample space here as well. Sample space is covering all the possible outputs, and whenever we are adding all the probabilities of all the possible outputs, obviously the output will be 1. Say for example, if you take the tossing of coin, then probability of head and probability of tail, whenever you are adding all the probabilities of all the outputs, you are absolutely getting 1. Simply if you are adding the probabilities whenever there is a tossing of a die, these examples are only for helping us to understand the concepts better. Whenever a die is tossed, then probability of 1 plus probability of 2 plus probability up to probability of 6 is 1, and where each probability is 1 by 6, 1 by 6, 1 by 6, and so on. Okay. So these two properties kindly remember. Now let me come back to probability density function again. Here I am going to calculate the value of k. I have given the value of k here for the rectangular or uniform probability density function. Let me calculate the value of k. So here if we see the second property, I am putting equation 2 here. If using this property, let me calculate the value of k. So in the second property, it is saying that integration minus infinity to infinity pdf, probability density function of dx, is equal to 1. So here from minus infinity to plus infinity, the PDF is only having one value k, and also the limits are from minus infinity to a, it is simply 0. So I am breaking it down the integral as minus 1 infinity to 0, minus 1 infinity to a 0 dx plus a to b k dx plus b to infinity 0 dx, because from the probability density function, if we see the graph above, from b above more than b, all the probability density function is taking a value of 0, and less than a, the probability density function is taking the value of 0. So just applying those values here, what we are getting is, and we have also taken the integration of probability density function over the entire real scale is simply 1. So let me equate this to 1. So the first term is simply becoming 0, and the last term is simply becoming 0. The central term I am taking a k outside because it is a constant. Then kx from a to b is equal to 1. So k into b minus a is equal to 1, or k can be written as 1 by b minus a. So this way we obtain the value of k as 1 by b minus a. This is for the probability density function using an example of uniform probability density. So let's go next. See, we have obtained the value of k. Now let us see what is probability distribution function for the continuous random variable. We have seen the probability distribution function for a discrete random variable that was taking the shape of a staircase. Now for the continuous random variable, if we are calculating the probability distribution function, the formula applied will be again the same. The symbol of probability distribution function for the continuous random variable, is the notational symbol, is simply given as fx of x, and the mathematical formula in order to calculate this one is integral minus infinity to x probability density function into dx. Here if you have observed our probability density function which I have taken at the starting of the slide, the rectangular probability density function. If you are taking the same rectangular probability density function, if you are applying the same PDF here in calculation of probability distribution function for the same, here we can say integral minus infinity to x, that rectangular function from a to b dx. I can write this one as integral minus infinity to a 0 dx plus a to x k dx plus, here the third term doesn't come because x we have considered between a and b. If suppose x is a and between a and b, let me separately mention here x is between a and b. If x is less than a, the probability density function at that point is simply 0, so fx of x also will be taking the value as 0. But if it is x is greater, if x is between a and b, then this formula is applied. So let us deduce the expression. K is a constant, let me take it outside, sir. Then here it becomes simply x. The limits are applied from a to x, so I can write it as k into x minus a. So that again k, we have obtained the expression for k in the expression 3 that I have written above. If you put simply the expression k here, it becomes 1 by b minus a into x minus a. So the first possibility, so probability distribution function is calculated for 3 possibilities. The first possibility is x is less than a. It is simply 0 because there is no probability density function existing for less than a. The second possibility is x is between a and b. For that one, we have obtained the value x minus a divided by b minus a. The third possibility is x is greater than b. Now let me calculate the probability distribution function for x is greater than b. So let's go to the next page here. So the values of probability distribution function is simply 0 for x is less than a, and whenever x is between a and b, it is x minus a divided by b minus a, and if it is x is greater than b, that we need to calculate now. So for x is greater than b, if we see, we are integrating over the area of this rectangle. For x is greater than b, simply we are integrating probability density function from a to b. So k is the value of the probability density function. So let me calculate that. Let me go to the next page here. So now let us see the value of the probability distribution function for value for x greater than b. Earlier we have seen for the x that is less than a, the probability distribution function is simply taking 0, because the reason is that there is no existence of density function for x is less than a. But for x is greater than a and less than b, then it follows that integration of minus infinity to x fx of x dx, where fx of x is actually taking the value k we have obtained earlier as 1 by b minus a, and whenever we are integrating dx, we will be getting x, and that integration is from minus infinity to x. So finally we are going to get the value x minus a divided by b minus a for x is between a and b. But for x is greater than b, we are trying to evaluate the probability distribution function. So for x is greater than b, integral minus infinity to x fx of x dx. So k is again 1 by b minus a, that's a constant that can be taken outside, and minus infinity to x. But the range of integration, whenever it is taken from minus infinity to a, the PDF is simply 0. So integral of that value will also be 0. There is no need to calculate from up to a. From a to b, we know that it is x minus a divided by b minus a. But for greater than b, then the range of integration is from a to b itself, because for greater than b, again the probability density function is again 0 and integral of 0 is again 0. So we will consider only from a to b. a to b, the k will be taken outside as 1 by b minus a, and a to b dx, integration dx is simply taking the form of x, and a to b is substituted there, that will be giving b minus a. So b minus a in the numerator and b minus a in the denominator will finally give the answer as 1. So for the values of x is greater than b, towards the right side of b, the value is constant at 1. For x is less than b and greater than a, that is simply x minus a divided by b minus a, that is taking the form of a ramp, again with the slope 1 by b minus a, that is a ramp signal with slope 1 by b minus a. And for x is less than a, as we have already evaluated, the distribution function value is simply 0. The reason is that the density function's value for x is less than a is 0. So here the probability distribution function plot is obtained. So the plot of probability distribution function of a continuous random variable is also continuous. So continuous random variable with a continuous probability density function is having the plot that is also continuous. The distribution function is also continuous. Earlier we have seen in the earlier slides, one of the slides earlier, for the discrete random variable with discrete probability density function which are given by impulses, the probability distribution function is taking the form of a staircase. But when it comes to the probability distribution function of continuous random variable, the probability distribution function is continuous, and for the rectangular distribution or the uniform distribution, the probability distribution function is like a ramp signal. Okay. Now we have seen what is the definition of probability distribution function, and we have developed the concept of probability distribution function, probability mass function, probability density function. Now let's go a little bit deeper into joint random variables. So as the name itself is indicating, there are some scenarios where just we have seen earlier that there are some kind of scenarios where joint joint events are considered using the symbol intersection. Say for example, probability of A intersection B is the joint probability of A and B. Events A and B. Similarly, here also fx of x comma y is actually gives us joint probability, not the probability, it is joint probability density function. Joint probability density function. Again, similarly along the same lines, there is something called as fx, capital Fx y x comma y, that is joint probability distribution function. In this case, the probability distribution is depending on both the variables. Instead of x alone or y alone, it is depending on both the variables x and y. So that is the reason it is called a joint probability distribution function. Now let's go deep into each of these things, these terms. So we are going to discuss another term called as conditional probability density function. Here, earlier we have seen this one, probability of A by B and B by A, which is actually given by probability of A intersection B divided by P of B, if we remember in the first class. Here it is called as conditional probability. Conditional probability of occurrence of A given that B is already occurred. Similarly, Fy in braces y by x is actually conditional probability density function. Conditional probability density function of y for a given x. Here also x is already given, and the evaluation of probability density function of y for a given x is called as conditional probability density function Fy of y by x. Now let us go into each of these terms and let us have some insight into these joint random variables and joint probability density function and joint probability distribution functions. Let's go to the next slide. So we shall continue with defining the joint probability density and distributive functions and joint random variables. So the joint probability distribution function is simply given by this way, and this is the mathematical equivalent of this joint probability distribution function is probability of random variable x is less than or equal to x and y is less than or equal to y. This is a joint probability distribution function, and the joint probability density function is given by this notation, and that is equal to double derivative of joint probability distribution function. Earlier we have seen the calculation of a single variable density function. We have seen that single variable distribution function fx of x is equal to integral of minus infinity to x the probability density function. So from this relation we can say that the probability density function fx of x is equal to d by dx of probability distribution function capital Fx of x. Similarly, on the similar lines, equation 2 is written. That means the joint probability density function is given by partial derivative, double derivative, first with respect to y, then with respect to x of probability distribution function p fx y x comma y. So this relation is obtained on the similar lines. Now let us see what is the conditional probability joint probability random variable or conditional joint probability density function. So it is the notation. Let me give the notation for conditional probability density function. The notation is fy of y by x. Here it is indicating the probability density function of y for a constant or for a fixed x, that is given by fx f y x comma y whole divided by fx of x, where the numerator term fxy x comma y is the joint probability density function. Denominator we know fx of x. And say for example, earlier we have seen statistical independence property. For joint events A and B, that is actually given by probability of A intersection B is equal to probability of A into probability of B. This property is satisfied whenever this A and B are statistically independent. And earlier we have seen another property called mutually exclusiveness. That also, let me put the statement here. A and B are mutually exclusive if A intersection B is simply 0. That means that if A is occurring, then B is not occurring, or if A is not occurring, then only B is occurring. So this is called as mutually exclusiveness, and probability of A intersection B is 0 if both A and B are mutually exclusive. But if for the case of independence, P of A intersection B is equal to P of A into P of B if A and B are statistically independent. Similarly, if A and B are statistically independent, here in the random variables we are dealing with x and y random variables. If x and y are statistically independent, then fxy of x comma y, the joint probability density function, is actually given by fx of x into fy of y. So if we are applying this property, statistical independence of random variables, which I am given by 4 in 3 above, what we get is the conditional probability density function fy of y by x is equal to fx of x into fy of y whole divided by fx of x, and simply fx of x and fx of x are cancelled. We are getting fy of y. So what we inference, I shall put some inference here. That inference is the conditional probability density function of y at a fixed x is simply f of y. The conditional probability density function of y for a fixed x is simply fy of y if x and y are independent random variables. Independent random variables. That means the conditional probability of occurrence of y for a fixed x is completely independent of x, and it is completely dependent on y itself if they are independent. So this is another conclusion. Let me put it as phi. So these joint probability density and conditional probability density and joint probability distributive functions are giving some insights about the joint probability random variables and their probability density and distributive functions. Now let us see what is evaluation of single random variable probability density function from joint probability density. Now let us see the process of evaluation of probability density function with respect to x, say fx of x, from the joint probability density fxy of x comma y. So this can be obtained using integration minus infinity to infinity, again integration minus infinity to x. Because there are two random variables, we need to apply two integrations, fxy of x comma y dx dy. So internal integration will be, the internal integral variable will be nearer to the internal integral, and external integration will be with respect to the external variable. So whenever we apply, we need to find a probability density with respect to one variable, we are going to integrate the joint probability density function with respect to other variable from minus infinity to infinity. So here once we evaluate this integral, now this integral need not be applied. The reason is that we are only calculating the probability density function with respect to x. Here this one is applied, that means this one is applied only if you are actually finding the probability distribution function with respect to x. Here it is the probability density function, so the second integral need not be applied if you are integrating. So let me write it again. Here a probability density function only with respect to x is obtained by integration of the probability density function fxy of x comma y with respect to y from minus infinity to infinity. And if you want the probability distributive function with respect to x, then yes, we have earlier written this expression with little bit mistake. We have to apply this equation. First we have to integrate everything with respect to y from minus infinity to infinity, then integral minus infinity to x fx comma y of xy into dx dy. So again here we see that if we differentiate this last expression number 6, then we are getting this one number 7. So if we differentiate number 6 on both sides, what we are getting is fx of x at the small pdf is equal to, here this integration with respect to x and this x integration with respect to x and that derivative with respect to x will be cancelling each other, and we will be finally obtaining this relation. So in a sense 7 and 6 are obtained by integration on both sides. So now let's go to the next page here. So in the earlier slide we have seen the expressions for probability distribution function only with respect to one variable x, which we have formed the equation number 6, and the probability density function only with respect to x, which we formed the equation number 7. So now in this further we will continue our discussion from here. So earlier we have seen when we are discussing only the probability density function with respect to x, we have discussed two properties. The first property is the probability density function is never less than 0 or it is never negative. This is one. The other property that we have seen is the integral minus infinity to infinity with respect to the random variable x probability density function is simply 1. So on the similar lines, similarly we can obtain the properties for joint probability density functions also. The property is the first one, application of the first on the similar lines. Analogously, the first property is joint probability density function fx comma y is always greater than or equal to 0. The second property is integral minus infinity to infinity with respect to y and with respect to x, minus infinity to infinity with respect to x, joint probability density function fxy of x comma y dx dy is simply is equal to 1. So these two properties again hold good for the joint probability density functions also. So let us by understanding these two properties, let's conclude this session. In this session we have discussed the joint probability definitions, and joint probability definitions, they are distribution and also density definitions. Joint conditional probability, property of statistical independence for joint random variables and associated probability functions. So in the next session what we are going to cover is, let me write the topics here. We are going to cover the basics of Bernoulli's experiment and binomial experiment and some other probability patterns or probability functions. So let me define the Bernoulli's experiment once here itself. Bernoulli's experiment is very simple one. If an experiment is having two outcomes and there is no other possibility, then the experiment is Bernoulli's. Suppose the outcome, the first outcome's probability is p, then obviously the next outcome's probability is 1 by p, 1 minus p. The reason is there are only two outcomes. So if the first outcomes probability is p, then obviously the other outcomes probability is 1 minus p, because the completeness is only having only two events, since the sample is p of sample is 1. Sample is having only two events. Let me say that is event 1 and event 2. So probability of sample is equal to probability of event 1 plus probability of event 2 minus probability of event 1 intersection event 2. But what happening is here, there is these two events, E1 and E2, are mutually exclusive. As they are mutually exclusive, P of E1 intersection E2 is equal to 0. So we can say probability of the sample is equal to P of E1 plus P of E2, and probability of sample is simply 1. So if probability of one of the events P of E1 is P, then the probability of the second event is P of E2 is equal to 1 minus P. So such a experiment is called as Bernoulli's experiment. The best example of the Bernoulli's experiment is, no need to explain much, tossing a coin. There are only two outcomes. The probability of one of the outcome is P, then the probability of the other outcome is 1 minus P, where P is half in the case of tossing a coin. Okay, now let's meet in the next lecture and continue our discussion with binomial experiment and further probability distributions.